A hammer is a tool meant to deliver an impact to an object. The most common uses for hammers are to drive nails, fit parts, forge metal and break apart objects. Hammers are often designed for a specific purpose, and vary in their shape and structure. The term hammer is also used for some devices that are designed to deliver blows, for example, the caplock mechanism of firearms. The hammer is a basic tool of many professions. The usual features are a handle and a head, with most of the weight in the head. The basic design is hand-operated, but there are also many mechanically operated models, such as steam hammers, for heavier uses. History: the use of simple hammers dates to about 2,600,000 BCE when various shaped stones were used to strike wood, bone, or other stones to break them apart and shape them. Stones attached to sticks with strips of leather or animal sinew were being used as hammers with handles by about 30,000 BCE during the middle of the Paleolithic Stone Age. The hammer's archaeological record shows that it may be the oldest tool for which definite evidence exists of its early existence. Designs and variations. A large hammer-like tool is a maul, a wood or rubber-headed hammer is a mallet, and a hammer with a cutting blade is usually called a hatchet. The essential part of a hammer is the head, a compact solid mass that is able to deliver the blow to the intended target without itself deforming. The opposite side may have a ball shape, as in the ball-peen hammer and the cow hammer. Some upholstery hammers have a magnetized face, to pick up tacks. In the hatchet, the hammer head is secondary to the cutting edge of the tool. The impact between steel hammer heads and the objects being hit can create sparks, which may ignite flammable or explosive gases. These are a hazard in some industries such as underground coal mining, or in other hazardous environments such as petroleum refineries and chemical plants. In these environments, a variety of non-sparking metal tools are used, primarily aluminium or beryllium copper hammers. In recent years, the handles have been made of durable plastic or rubber, though wood is still widely used. Popular hand-powered variations include ball-peen hammer, or mechanic's hammer, boiler scaling hammer, brass hammer, also known as non-sparking hammer or spark-proof hammer and used mainly in flammable areas like oil fields, brick hammer, carpenter's hammer, such as the framing hammer and the claw hammer, and pin hammers, cross-peen hammer, having one round face and one wedge-peen face. Drilling hammer, a short-handled sledgehammer originally used for drilling in rock with a chisel. The name usually refers to a hammer with a 2-4 lb head and a 10-inch handle, also called a single jack hammer because it was used by one person drilling, holding the chisel in one hand and the hammer in the other. In modern usage, the term is mostly interchangeable with engineer's hammer, although it can indicate a version with a slightly shorter handle. Engineer's hammer, a short-handled hammer, originally an essential component of a railroad engineer's toolkit for working on steam locomotives. Typical weight is 2-4 lbs with a 12 to 14-inch handle. Originally these were often cross-peen hammers, with one round face and one wedge-peen face, but in modern usage the term primarily refers to hammers with two round faces. Gavel, used by judges and presiding authorities to draw attention, geologist's hammer or rock pick, joiner's hammer, or Warrington hammer, knife-edged hammer, its properties developed to aid a hammerer in the act of slicing whilst bludgeoning. Lathe hammer, a tool used for cutting and nailing wood. Lath, which is a small hatchet blade on one side and a hammer head on the other. Lump hammer, or club hammer. Mallets, including the rubber hammer and dead blow hammer. Railway track keying hammer, rock climbing hammer, sledgehammer, soft-faced hammer, splitting maul, stonemason's hammer, tinner's hammer, upholstery hammer, welder's chipping hammer. Mechanically powered hammers. Mechanically powered hammers often look quite different from the hand tools, but nevertheless most of them work on the same principle. They include hammer drill, that combines a jackhammer-like mechanism with a drill, high-frequency impact treatment hammer for after-treatment of weld transitions, jackhammer, steam hammer, trip hammer. In professional framing carpentry, the manual hammer has almost been completely replaced by the nail gun. In professional upholstery, its chief competitor is the staple gun. Tools used in conjunction with hammers: anvil, chisel, star drill, punch, wood splitting maul, can be hit with a sledgehammer for splitting wood. Wood-splitting wedge, hit with a sledgehammer for splitting wood. Physics of hammering. Hammer as a force amplifier. A hammer is basically a force amplifier that works by converting mechanical work into kinetic energy and back. In the swing that precedes each blow, a certain amount of kinetic energy gets stored in the hammer's head, equal to the length d of the swing times the force F produced by the muscles of the arm and by gravity. When the hammer strikes, the head gets stopped by an opposite force coming from the target, which is equal and opposite to the force applied by the head to the target. If the target is a hard and heavy object, or if it is resting on some sort of anvil, the head can travel only a very short distance d before stopping. Since the stopping force F times that distance must be equal to the head's kinetic energy, it follows that F will be much greater than the original driving force F roughly, by a factor dd. In this way, great strength is not needed to produce a force strong enough to bend steel, or crack the hardest stone. Effect of the head's mass. The amount of energy delivered to the target by the hammer blow is equivalent to 1/2 the mass of the head times the square of the head's speed at the time of impact. While the energy delivered to the target increases linearly with mass, it increases quadratically with the speed. High-tech titanium heads are lighter and allow for longer handles, thus increasing velocity and delivering more energy with less arm fatigue than that of a steel-head hammer of the same weight. As hammers must be used in many circumstances, where the position of the person using them cannot be taken for granted, trade-offs are made for the sake of practicality. In areas where one has plenty of room, a long handle with a heavy head can deliver the maximum amount of energy to the target. It is not practical to use such a large hammer for all tasks, however, and thus the overall design has been modified repeatedly to achieve the optimum utility in a wide variety of situations. Effect of the handle. The handle of the hammer helps in several ways. It keeps the user's hands away from the point of impact. It provides a broad area that is better suited for gripping by the hand. Most importantly, it allows the user to maximize the speed of the head on each blow. The primary constraint on additional handle length is the lack of space in which to swing the hammer. This is why sledgehammers, largely used in open spaces, can have handles that are much longer than a standard carpenter's hammer. The second most important constraint is more subtle. Even without considering the effects of fatigue, the longer the handle, the harder it is to guide the head of the hammer to its target at full speed. Most designs are a compromise between practicality and energy efficiency. Too long a handle, the hammer is inefficient because it delivers force to the wrong place, off target. Too short a handle, the hammer is inefficient because it doesn't deliver enough force, requiring more blows to complete a given task. Recently, modifications have also been made with respect to the effect of the hammer on the user. A titanium head has about 3% recoil and can result in greater efficiency and less fatigue when compared to a steel head with up to 30% recoil. Handles made of shock-absorbing materials or varying angles attempt to make it easier for the user to continue to wield this age-old device, even as nail guns and other powered drivers encroach on its traditional field of use. Effect of gravity. Gravity exerts a force on the hammer head. If hammering downwards, gravity increases the acceleration during the hammer stroke and increases the energy delivered with each blow. If hammering upwards, gravity reduces the acceleration during the hammer stroke and therefore reduces the energy delivered with each blow. Some hammering methods, such as pile drivers, rely entirely on gravity for acceleration on the downstroke. Warhammers. A warhammer is a late medieval weapon of war intended for close combat action. Symbolic hammers. The hammer, being one of the most used tools by Homo sapiens, has been used very much in symbols and arms. In the Middle Ages it was used often in blacksmith guild logos, as well as in many family symbols. The hammer and pick is used as a symbol of mining. A well-known symbol with a hammer in it is the hammer and sickle, which was the symbol of the former Soviet Union and is very interlinked with communism-socialism. The hammer in this symbol represents the industrial working class. The hammer is used in some coat of arms in socialist countries like East Germany. In Norse mythology, Thor, the god of thunder and lightning, wields a hammer named Mja paragraph LNIR. Many artifacts of decorative hammers have been found, leading modern practitioners of this religion to often wear reproductions as a sign of their faith. Judah Maccabee, the hammer. In American folklore, the hammer of John Henry represents the strength and endurance of a man. The hammer in the song "If I Had a Hammer" represents a relentless message of justice broadcast across the land. The song became a symbol of the American civil rights movement. Gallery. See also. Category, Tools, References. External links, Hammer types, images and descriptions. The Hammer Museum, Choosing a Hammer. Popular Science, June 1960, ppA 164–167.